The telegram arrived at the War Department in Washington on a Tuesday morning in February 1942, and within hours it had been classified, copied, and distributed to every ordnance officer who held a secret clearance. The message was simple and devastating. British armored units in North Africa had engaged German forces near a place called Bir Hakeim, and the results had been catastrophic. Matilda tanks that had once seemed invincible against Italian armor were now burning hulks scattered across the desert. The Germans had a new weapon, something that punched through British steel as if it were wet cardboard, something that left perfectly circular entry holes with edges so clean they looked machined rather than melted. The British called it the Devil's Finger. The Americans would soon learn to call it by its German name, Panzer Granate 40. In a cramped laboratory at the Aberdeen Proving Ground in Maryland, a young metallurgist named Harold Rosenberg held a fragment of German ammunition in his gloved hands and tried to understand what he was looking at. The fragment had been recovered from a destroyed British tank and shipped across the Atlantic at considerable expense and risk. It was small, no larger than a pencil stub, but it was extraordinarily heavy. Rosenberg placed it on a precision scale. The density reading made him check his instruments twice. This was not steel. This was not iron. This was something else entirely. The fragment was tungsten carbide. Rosenberg knew the material. Every metallurgist in America knew it, at least in theory. Tungsten carbide was a compound of tungsten and carbon sintered together at extreme temperatures and pressures to create one of the hardest substances known to science. It was used in cutting tools, in mining equipment, in the dies that drew copper wire for electrical cables. But no one in the American ordnance community had seriously considered using it in ammunition. The material was too expensive, too difficult to machine, and most importantly, too scarce. America had tungsten mines in Nevada and California and Colorado, but the quantities produced were nowhere near sufficient for military use on the scale that war would demand. The Germans, apparently, had solved that problem, or at least they had solved it well enough to equip their anti-tank guns with rounds that could defeat any armor the Allies possessed. Rosenberg wrote his report that night, working until dawn to compile the technical specifications he had derived from the fragment. His conclusions were stark. The German PZGR-40 round used a sub-caliber penetrator of tungsten carbide encased in a lightweight body of aluminum alloy. When the round struck armor, the soft outer shell deformed and fell away, while the dense tungsten core continued forward at tremendous velocity, concentrating all of its kinetic energy into a single point of impact. The physics were elegant and brutal. The denser the penetrator, the better it retained velocity. The harder the penetrator, the less it deformed on impact. Tungsten carbide was both dense and hard. It was, in fact, almost perfectly suited to the task of killing tanks. The problem was that America did not have enough tungsten to fight a war. This was not entirely an accident of geology. America had tungsten deposits, though they were modest compared to the vast reserves in China, which at that time produced more than half of the world's supply. But the real reason American industry lacked tungsten carbide capacity was not geology. It was a business arrangement that had been signed in the boardrooms of two corporations separated by an ocean and joined by a shared desire for profit. In 1928, the Friedrich Krupp Gesellschaft of Essen, Germany, and the General Electric Company of Schenectady, New York, had concluded an agreement that would shape the course of the war that neither company could yet imagine. Krupp held the fundamental patents on the commercial production of cemented tungsten carbide, a material they marketed under the trade name Widia, short for V-Diamant or like diamond. General Electric, through its subsidiary, the Carbide Company, had developed competing processes that might have challenged the Krupp patents in court. Instead of fighting, the two corporations chose to cooperate. They divided the world between them. Under the terms of their agreement, Krupp would control the sale of tungsten carbide everywhere except the United States and Canada, which belonged to General Electric. In exchange, GE would refrain from exporting tungsten carbide products to any country in Krupp's territory. The practical effect of this arrangement was that American industry became almost entirely dependent on Carballoy for tungsten carbide tooling, and Carballoy, freed from competition, raised its prices accordingly. Before the agreement, tungsten carbide sold for approximately $50 per pound. After the agreement, Carballoy charged $450 per pound, an increase of nearly 900%. At these prices, few American manufacturers could afford to tool their factories with tungsten carbide equipment. They made do with inferior alternatives, molybdenum-tipped tools that wore out faster, high-speed steel that required more frequent replacement. German industry, by contrast, had abundant access to tungsten carbide at prices that reflected competitive market conditions. When the war began, German machine shops were equipped with cutting tools that lasted 10 times longer than their American counterparts. German tank factories produced vehicles with a precision that American factories could not match, and German ammunition factories produced anti-tank rounds that could destroy any Allied vehicle they encountered. In April 1942, as Rosenberg's report circulated through the War Department, the United States Senate convened a special hearing to investigate the Carballoy monopoly. The Truman Committee, led by Senator Harry S. Truman of Missouri, summoned GE executives to testify about their arrangements with Krupp. The testimony was damning. Letters were introduced into evidence that showed GE executives consulting with Krupp on which American companies should be denied licenses to produce tungsten carbide. Memoranda documented agreements to fix prices and restrict output. One particularly inflammatory exhibit was a communication in which Krupp instructed GE that it was prohibited from exporting tungsten carbide to the Soviet Union, a message that had been sent in 1939, when the Soviet Union was not yet an enemy of Germany. The executives of Carballoy denied any wrongdoing. William G. Robbins, the company's president, stood before the committee and declared that he refused to be called un-American. The senators were unimpressed. Senator Truman noted dryly that GE's arrangement with Krupp had resulted in a drastic shortage of tungsten carbide at a moment when American forces needed every advantage they could get. The committee's final report concluded that the cartel agreement had retarded the development of the American machine tool industry and had left the United States unprepared for the industrial demands of modern warfare. But congressional condemnation would not defeat German tanks. Something more practical was required. The solution began to take shape in a converted warehouse on the outskirts of Detroit, where a team of engineers from the Ordnance Department had been assigned the task of developing American armor-piercing ammunition that could compete with the German PZGR-40. The team leader was a quiet man named Ralph Palmer, who had spent the previous decade designing automotive engine components for Chrysler. He knew nothing about tank warfare when he arrived in Detroit. Within 6 months, he would become one of the foremost experts in the country on terminal ballistics. Palmer's first task was to acquire enough tungsten carbide to conduct meaningful experiments. This proved nearly impossible. The Carballoy Company was legally obligated to supply the military with whatever quantities were needed, but needed was a flexible term, and civilian demand for cutting tools had not evaporated simply because a war was being fought. Palmer found himself competing for tungsten allocations with automobile factories retooling for tank production, aircraft plants building bombers, and shipyards constructing destroyers. Everyone needed tungsten carbide. No one had enough. In desperation, Palmer contacted the War Production Board and requested permission to pursue alternative sources. The board granted his request and provided him with a list of companies that might be able to supply raw tungsten or tungsten compounds. Most of the names on the list were mining operations in South America, where tungsten deposits had been identified but not yet developed. One name, however, caught Palmer's attention. It was a small firm in Cleveland, Ohio, that claimed to have developed a new process for producing tungsten carbide from recycled industrial scrap. The firm was called the Metallurgical Products Company, and its founder was a Hungarian immigrant named Philip McKenna. McKenna had arrived in the United States in 1935 with a degree in metallurgical engineering from the Technical University of Budapest and a conviction that American industry was wasting enormous quantities of valuable materials. He had spent the intervening years developing techniques for recovering tungsten from worn cutting tools, grinding dust, and other industrial waste streams. By 1941, his small factory was producing several hundred pounds of recycled tungsten carbide per month, a trivial quantity by wartime standards, but proof that the process worked. Palmer visited McKenna's factory in March 1942 and left with a contract in his briefcase. The War Production Board would fund an immediate expansion of McKenna's operation, and McKenna would dedicate his entire output to military applications. Within 6 months, the Metallurgical Products Company had grown from 12 employees to over 200. Within a year, it was producing more tungsten carbide than any single facility in the country except Carbolloy itself. But tungsten alone would not win battles. The Germans had not merely discovered a new material, they had invented a new type of ammunition that exploited the material's unique properties. American engineers would have to design their own version from scratch. The first American attempt at a tungsten core armor-piercing round was designated the T-30. It was a 37mm projectile intended for the anti-tank guns mounted on light tanks and armored cars. The design was straightforward, a small cylinder of tungsten carbide, roughly the diameter of a pencil, encased in a body of stamped aluminum. When fired, the round was supposed to achieve a muzzle velocity of approximately 2,900 feet per second, fast enough, Palmer calculated, to penetrate the frontal armor of a Panzer III at combat ranges. The first test firings were conducted at Aberdeen in August 1942. The results were not encouraging. Of 20 rounds fired, 7 shattered on impact without penetrating the target plate. 3 more tumbled in flight and struck the target at oblique angles, producing spectacular sparks but no penetration. Only 10 rounds performed as designed, and even those showed significant variability in their terminal effects. Palmer collected the fragments and studied them under a microscope. The tungsten carbide cores were cracking along crystalline boundaries, breaking apart under the stress of impact rather than punching through as a unified mass. The problem, Palmer eventually determined, was not the tungsten carbide itself, but the method by which it had been bonded to the aluminum body. The manufacturing process required heating the components to extremely high temperatures, which caused differential expansion between the carbide core and the aluminum shell. When the assembly cooled, microscopic stresses developed at the interface between the two materials. Under the shock of impact, these stresses caused the carbide to fracture catastrophically. Palmer spent the autumn of 1942 experimenting with different bonding methods. He tried brazing, soldering, mechanical interference fits, and various combinations thereof. He consulted with specialists in ceramic engineering, powder metallurgy, and high-temperature chemistry. He read every technical paper he could find on the properties of tungsten carbide and the behavior of composite materials under shock loading. Gradually, painfully, he developed an understanding of what was happening inside his ammunition and how to prevent it. The breakthrough came in January 1943 when Palmer discovered that a thin layer of copper deposited between the tungsten carbide core and the aluminum body could absorb the differential stresses without transmitting them to the brittle carbide. The copper acted as a cushion, deforming plastically under load while the carbide remained intact. When Palmer tested this new design, the results were dramatically improved. Of 20 rounds fired, 18 penetrated the target plate cleanly. The tungsten cores emerged from the far side of the armor almost undamaged, having punched through steel that would have stopped any conventional round. The new design was designated the T4, later standardized as the M93 HVAP, high-velocity armor-piercing. Production began in the spring of 1943, but the quantities were pitifully small. Tungsten remained scarce despite McKenna's recycling operation and desperate efforts to develop new mines in the American Southwest. The Army Production Board calculated that even if every available source of tungsten were dedicated entirely to ammunition production, the United States could produce no more than 50,000 HVAP rounds per month. That sounded like a large number until you considered that the Army expected to have over 10,000 tanks in combat by the end of 1944, and each tank carried an ammunition load of approximately 70 rounds. The allocation decision was brutal but logical. HVAP rounds would be reserved for tank destroyer battalions, whose specialized mission was hunting enemy armor. Regular tank units would continue to receive standard armor-piercing ammunition with steel cores, rounds that were adequate against Panzer IIIs and IVs, but increasingly ineffective against the newer Panthers and Tigers that German factories were producing in growing numbers. The tankers would have to make do with inferior ammunition and superior tactics. They would have to rely on flanking maneuvers, coordinated artillery support, and the sheer numerical advantage that American industrial capacity provided. They would have to accept losses that better ammunition might have prevented. The first HVAP rounds reached the European theater of operations in September 1944, just in time for the Battle of Arracourt. The engagement took place in the Lorraine region of eastern France, where elements of Patton's Third Army had established a bridgehead across the Moselle River. The Germans counterattacked with two Panzer brigades equipped primarily with Panther tanks, vehicles that outclassed the M4 Sherman in almost every measurable way. The Panther's 75mm gun could penetrate a Sherman's armor at ranges exceeding a mile. The Sherman's 75mm gun could barely scratch a Panther's frontal armor at point-blank range. The American commander at Arracourt was Colonel Bruce Clark, a West Point graduate who had spent the previous 2 years learning everything he could about armored warfare. Clark knew his Shermans could not defeat Panthers in a straight-up gunnery duel, so he refused to fight one. Instead, he used the terrain, rolling hills covered with dense morning fog, to position his tanks in ambush locations where they could engage the Panthers from the flank or rear. He deployed his tank destroyers, equipped with the precious HVAP rounds, at key choke points where German armor would have to pass. The battle lasted 11 days. When it was over, the Germans had lost nearly 200 armored vehicles, including over 100 Panthers. The Americans had lost fewer than 30 tanks. The HVAP rounds had proven decisive at critical moments, allowing American gunners to penetrate Panther armor at ranges where conventional ammunition would have bounced harmlessly off the sloped glacis plate. But the real lesson of Arracourt was not about ammunition. It was about tactics, training, and the willingness to fight smart when you could not fight fair. The German tankers at Arracourt had better vehicles and bigger guns. What they lacked was experience, intelligence about American positions, and the flexibility to adapt when their initial attacks failed. They advanced in neat formations through the fog, presenting their side armor to American gunners who had spent months practicing exactly this kind of ambush. They fought as if superior equipment guaranteed victory. They died in their Panthers, burning in vehicles that should have been invincible. The tungsten carbide cores that cracked Panzer's steel were important. They gave American tankers a capability they had previously lacked, the ability to defeat heavy German armor at combat ranges with a single well-aimed shot. But the cores alone did not win battles. What won battles was the integration of those cores into a broader system of warfare that included scouting, communication, air support, artillery coordination, and the hard-won tactical wisdom of commanders who understood that in war, the side that adapts fastest usually wins. After the war, when the archives were opened and the full scope of the GE Krupp cartel became public knowledge, there was talk of prosecution and punishment. The Justice Department assembled a case that documented in exhaustive detail how the two corporations had conspired to restrict American access to a critical war material. In 1947, the case finally came to trial. The government presented its evidence. The defense presented its excuses. The jury deliberated for several days and then returned a verdict of guilty on multiple counts of antitrust violation. The punishment was a fine. General Electric paid $40,000. The individual executives who had negotiated the cartel agreements received suspended sentences and expressions of judicial displeasure. No one went to prison. No one's career was ruined. The war was over, the victory won, and the country was eager to move forward into a future that promised prosperity and peace. The Tungsten scandal became a footnote in histories that focused on battles and generals and the grand sweep of strategy. The engineers who had solved the tungsten problem were forgotten, their contributions absorbed into the anonymous mass of American industrial might that textbooks invoked without explanation. But somewhere in the archives of the Army Ordnance Department, there is a box of documents that tells a different story. There are memos from Ralph Palmer describing his frustration with Carbide's pricing and his elation when McKenna's recycling process proved viable. There are test reports from Aberdeen showing the progression from the failed T-30 to the successful M-93. There are production schedules and allocation tables and after-action reports from Arracourt and a dozen other battles where HVAP rounds made the difference between victory and defeat. And there is a letter dated November 1944 from a tank destroyer crew commander named Staff Sergeant James Riley. Riley's unit had been equipped with the new M18 Hellcat, a fast and lightly armored vehicle whose only advantage over German tanks was its high-velocity gun and the HVAP ammunition that gun could fire. In his letter, Riley describes an engagement near the German border in which his crew destroyed a Panther tank with a single round at a range of 800 yards. The Panther had been advancing toward an American infantry position, its 75mm gun traversing to engage. Riley's gunner put an HVAP round through the Panther's turret face. The tungsten core punched through 120mm of armor and detonated the ready ammunition inside. The Panther exploded. "We didn't know what was in those rounds," Riley wrote. "They told us they were special. They told us to save them for emergencies. When I saw what that round did to that Panther, I understood why they were so hard to get. Someone, somewhere, had figured out how to put a fist through steel. I don't know who they were, I never met them, but I'm alive because of what they built." Philip McKenna went on to found Kennametal Incorporated, which became one of the largest manufacturers of tungsten carbide products in the world. Ralph Palmer returned to the automotive industry after the war and spent the rest of his career designing engine components. Harold Rosenberg, the metallurgist who first analyzed the German PZGR-40 fragment, became a professor at MIT and trained a generation of materials scientists. None of them became famous, none of them received medals or monuments or the recognition that military historians reserve for commanders and strategists. But they won a battle that was fought in laboratories and factories, in recycling plants and proving grounds, in the spaces where physics met engineering, and engineering met the brutal demands of war. They took a problem that seemed impossible. America had no tungsten, and they found a way around it. They invented, adapted, improvised, and delivered. They put tungsten carbide cores into the hands of American tankers who needed them to survive. The war was won with many weapons: rifles and artillery, bombers and battleships, courage and sacrifice on a scale that defies comprehension. But among those weapons were small cylinders of sintered metal no larger than a man's finger that flew through the air at 3,000 feet per second and punched holes in Panzer steel. Those cylinders were made by men whose names history forgot. from materials that America was not supposed to possess, using processes that had to be invented under pressure and perfected in haste. They called it the devil's finger when it was aimed at them. When Americans fired it back, they called it tungsten, wolfram carbide, names for a metal that was harder than diamond and scarcer than gold. They called it the great equalizer, the Panther killer, the round that gave a Sherman a chance against a tiger. They called it many things, but mostly they just called it ammunition, and they wished they had more.